Welcome to This Explainer. Today, we're doing something really exciting. We are going to dive headfirst into the highly technical, math-heavy world of automotive design by literally building a vehicle entirely from the inside out. We're looking past the shiny exterior paint and those comfortable leather seats to examine the fundamental structural skeleton that actually makes a machine work.
So, here's our roadmap for today. We'll start with the human-centric foundation, move on to designing the vehicle's legs, build out the structural skeleton, put it through some brutal physical testing and optimization, and finally wrap up with the future of chassis design.
All right, Section 1, the human-centric foundation. It's kind of ironic, but the absolute most complex engineering constraint in any vehicle is actually the human body. Before a single piece of metal is drawn up or cut, engineers have to establish the spatial requirements of the passengers. To do this, engineers use this wild mechanical fixture called the SAE J826 machine. Its whole job is to simulate the exact weight distribution and posture of a 50th percentile adult male. By defining a specific pivot axis between the torso and the thigh, engineers lock in what's known as the H point. This becomes the central datum coordinate, literally the 0, 0, 0 point, for the vehicle's entire 3D spatial reference system. Everything else, and I mean everything from the roof rails down to the steering wheel, is built around this exact point in space.
The extremes of automotive packaging are pretty wild when you compare different vehicles. A high-performance sports car, for instance, demands a super low center of gravity, meaning an exhausting 135mm chair height. It even forces a highly reclined back angle of up to 35 degrees just to keep the roofline aerodynamic. Sure, it makes getting in and out kind of a workout, but hey, that's a compromise performance drivers accept. On the flip side, a commercial van prioritizes visibility and space, sitting at a towering 425mm height. That upright posture drastically shrinks the required footprint for the cabin, which maximizes cargo space in the back.
Moving right along to Section 2, designing the vehicle's legs. Now that our human driver is firmly anchored in the digital space, we have to attach the legs and joints by mapping out the suspension. Because obviously, the chassis doesn't operate in a vacuum. It's completely dependent on how it connects to the road.
These exact 3D coordinates dictate how the tire tracks the pavement during its travel, and precision here is absolutely paramount. Imagine shifting a tire rod by just 1 single millimeter. That tiny change can introduce dangerous bump steer, meaning the car could literally steer itself when you hit a pothole at highway speeds. To avoid that, engineers calculate specific hardpoints for the suspension links to manage a massive multivariable geometry puzzle. They're dialing in camber gain to keep the tire tread flat during heavy cornering, and anti-dive geometry, which ingeniously uses braking forces to stop the front of the car from plowing downward when you hit the brakes.
But before we design the structural skeleton to actually hold these suspension legs, we really have to pause and ask a fundamental engineering question. Why go through all the trouble of making the vehicle's frame so incredibly rigid?
Well, the magic number is 10x. To guarantee our suspension geometry stays predictable, the structural chassis has to boast a torsional stiffness that is at least 10 times greater than the suspension's combined roll rate. This prevents the frame itself from twisting like a giant metal spring and lifting tires during heavy cornering. Think about it. If the chassis bends before the suspension springs even compress, all those precise 3D kinematic hardpoints we just mapped out, yeah, they're instantly thrown completely out of alignment.
Okay, Section 3, building the structural skeleton. Let's look at how all this translates into the physical materials and shapes that form the vehicle's bones. We know where the driver sits, we know where the suspension mounts, and we know it needs to be stiff. So how do we actually build the thing?
Your everyday passenger sedan uses what's called a monocoque, which is a highly efficient, robotically welded structure. It actually uses the exterior sheet metal and interior reinforcements as the primary load-bearing members. It's incredibly perfect for mass production. On the other hand, low-volume race cars rely on highly intricate, labor-intensive tubular space frames or carbon fiber sandwich panels. A space frame resolves forces strictly as pure tension and pure compression through individual high-strength tubes.
And the materials they use. The contrast is just fascinating. You can use baseline steel for a rugged truck ladder frame, or you could spend up to 6 times more for ultra-lightweight carbon fiber prepreg to dramatically drop a Formula car's mass while skyrocketing its stiffness. Aluminum is a fantastic middle ground with a high specific stiffness, but honestly, nothing beats carbon fiber sandwich panels. By bonding incredibly thin carbon skins to a thick, low-density honeycomb core, engineers can drastically increase bending stiffness with almost zero penalty to the mass.
Now, this brings us to topology optimization, specifically a dense mathematical concept called the SIMP method.
Why does this matter to you? Because when you're dealing with wildly expensive materials, you absolutely cannot afford to carry dead weight. The SIMP method mathematically penalizes intermediate densities. It essentially forces the computer to give engineers a stark black and white solution. You either need solid material here, or you leave an empty void.
Basically, this software puts the car on a ruthless digital diet. It matters because it allows engineers to digitally shave away every single ounce of fat, optimizing the skeleton to endure simulated frontal and side crash impacts way before a physical part is ever manufactured. It designs progressive crumple zones in the front rails to absorb energy while simultaneously reinforcing the side door beams to stay incredibly rigid, protecting the passenger survival cell.
Section 4. Optimization and Physical Testing. Okay, so we've joined our optimized, dissimilar materials. And because traditional fusion welding simply cannot bond steel directly to aluminum without making it dangerously brittle, we use cold techniques like self-piercing rivets and aerospace-grade structural adhesives. But the real truth comes out during brutal physical validation off the computer screen.
To isolate and test the raw strength of the frame, engineers literally replace the suspension springs with solid steel tubes. They strap the chassis to a rig, clamp down the rear axle, and apply massive twisting forces through a front lever beam. Then, they use precision dial indicators along the vehicle's sills to record local vertical displacements. It requires absolute precision. In fact, if the fixed rear end rotates beyond 20% of the front end's rotation, the whole test is completely invalid.
The target here? To pass regulatory standards and guarantee safety, the structural skeleton must rigidly resist this torque without excessive bending, hitting a torsional rigidity of at least 4,000 Newton-meters per degree over the wheelbase. This proves it can survive a lifetime of dynamic road fatigue. It validates the cyclic loading requirements, guaranteeing that your daily commute won't result in microcracks forming around weld toes or highly stressed joints over the years.
Finally, Section 5. The Future of Chassis. To wrap up our explainer today, we need to look at how electrification and modern technology are radically altering this traditional automotive anatomy. Everything we just covered? Those standard rules are currently being rewritten.
For instance, we're seeing the rapid rise of cell-to-chassis architectures. Here, the massive electric battery is no longer just cargo you bolt in. It's bonded with high-strength structural adhesive directly into the frame, acting as a primary load-bearing member. It is a brilliant leap forward. Plus, we're seeing e-corner modules that consolidate the steering, braking, and drive motors directly inside the wheel hubs. This actually shifts the structural load concentrations from the center of the car directly out to the corners.
But here's the catch. While this deep integration creates an incredibly stiff and lightweight machine, it leaves us with a compelling trade-off. If the battery is permanently bonded to the skeleton using adhesives with shear strengths over 20 megapascals, what happens to serviceability and recycling when the vehicle reaches the end of the road? Non-destructive disassembly becomes incredibly difficult. So, are we designing vehicles that perform better than ever before but are effectively impossible to repair after a minor impact? It's the ultimate engineering puzzle, and one that the entire automotive industry is racing to solve right now.